Now what I'd like to do is develop some of the mathematical or geometric relationships proposed with the model. And this first series of videos will deal with the expansion of observable space, where a volume of space varies to the square of the absolute time elapsed. And it's probably necessary to explain some of the relationships and terminology going to be used. And this is illustrated in this following example, in which let's say a pizza with a ruler and the pizza is being measured by a local ruler at T1. T1 refers to some point in the past. And then at some time in the future, T2, the pizza has expanded and so has the ruler. So relative measures of length have maintained their proportional relationship in this model. And notice that the notation used is to use a lowercase letter to represent a relative measure and a capitalized to represent an absolute measure. Now, if we adopt an eye of God perspective, it is possible to see that the pizza has expanded, and if it arbitrarily is chosen, that the size of this ruler in the past is used to represent the size of the pizza in the future. The eye of God perspective can see that now the pizza is 1 2/3 times bigger than it was at T1. Now this introduces some of the terminology going to be used, absolute and relative measures of distance, and there will be as time as well. Now, the basic formula, and I know formulas can be kind of dry, and what I hope though is that eventually there'll be some appreciation for how this is actually describing a kind of geometric relationship, no different than what you'd see in a multifaceted kind of a diamond kind of a thing, all based on well, it starts off very simply. Here we have the fundamental relationship that a volume of space-time geometrically varies to the square of the absolute time elapsed. Now, the volume of any object the volume is equal to some constant times a linear dimension measure representative of that object cubed. For example, the radius of a sphere, the length of one side of a cube, the size of a femur bone of a human being. And you can pick that linear measurement and get some sort of relationship. If you cube it times some constant, you're going to get some representative measure of the volume. This is characteristic of any volume. Now, this inverse k is somewhat arbitrary. We just made it so that the following formulas were easier to write, but the 1 over k is just a k. Now, since this describes how the volume varies over time, and this describes the actual relationship of volume, the two can be equated at a particular moment in time. So the volume is equal to some constant times d cubed, some representative distance measure of the object cubed, times the absolute measure of time squared, which can be algebraically manipulated into d cubed equals k times t squared. And those who are familiar, this looks amazingly like Kepler's law, which indeed it will be shown it does result in that relationship. But anyways, this can now be algebraically expressed as the distance measure on a volume would be some constant times the absolute age of whatever the object raised to the 2/3 power of time. So now what this would look like, well actually let me go over to show a picture of what this would look like. Okay, so here we have a volume of space with a distance measure at one point in T1 in the past, and then as time goes by the distance measure similarly has changed, and it would vary to the 2/3 power of absolute time. And so you kind of get an idea. Here's the beginning of time, here's T1, here's T2, and how the volume this volume would vary to the square. Squaring the absolute. Okay, now let's go back to the development of the equations. Now we don't really know the value of k. In fact, I put inadvertently when I was putting the paper together, I included the calculation what k was, but it was a little bit premature although it's explained later on. Now, we don't really know what the value of k is, but we do know that at t1 it does have a definite size, d1. And we know that at t2 we can predict what its size would be. So because of the geometry of the model, we can divide one by the other, thereby eliminating the k, and we have d1 over d2 is equal to, I call this the absolute ratio of time, or the ratio of time to the 2/3 power. Now, we can derive some additional relationships. For example, the distance between the 2 points varies over time. So if we take the first derivative of it, we have a velocity relationship of how the velocity of expansion would vary over the course of time. It would be k to the 2/3 t to the divided by t to the 1/3 power, or t to the minus 1/3 power. And then if we take the derivative of that, we'd have how the relationships would change. So if with velocity. So what this is specifically describing is the rate. If you stood here and measured over here on this side, how fast this point would be moving away from that point. And then at another point in time, we'd have how fast this measure is changing relative to that measure, d2. We would have a v2. Similarly, if we take the derivative again, we have the accelerative term. So the double derivative of how the distance measured establishes the accelerative term. Now, I adapted a notation to make this a little bit simpler to draw. This always doing d1 over d2 is a little laborious. So what I did here is this d with a bar sign, underline sign underneath it, means d1 over d2 is equal t1 over t2 raised to the 2/3 power. It just, instead of writing this all the time, which is all these 1s and 2s and one over the other, I adopted this notation. The earlier measure is over the later measure, and for each one of the terms. It makes it a little bit easier to manipulate the relationships. And now,